Okay, calculus 15.2 is line integrals. So a classic property of, for example, gravitational fields is that subject to certain physical constraints, the work done by gravity on an object moving between 2 points in the field is independent of the path taken by the object. One of the constraints is that the path must be a piecewise smooth curve. We know that for a plane curve C in 2 dimensions, it's smooth when both partial derivatives are continuous and not zero except possibly on the endpoints. Similarly, a space curve has the same rules. A curve C is piecewise smooth when the interval AB can be partitioned into a finite number of subintervals, on each of which C is smooth. So, as an example, find a piecewise smooth parametrization of the graph of C shown in the picture to the right. So it travels from 0, 0, 0 to 0, 2, 0, then to 1, 2, 0, and then to 1, 2, 1. So basically it's taking the travel from 0, 0, 0 to 1, 2, 1 and fixating it, just moving in, looks like the y direction first, then the x direction, then the z direction. So first things first, if we're moving 3 separate lines, we're going to do 3 separate intervals for t. It's convenient to let t just be a 1 second interval each time because it just makes it easier to figure out what's happening in our relationship to time for each of our variables. So our first function, well, since x and z aren't moving at all, we'll let them both be 0. Now y is going from 0 to 2 over 1 second, so y should just be 2t, because at 0 it's 0, but then at 1 it's 2. Second function, only y is now just 2, and z is 0, because neither of those is going to move between this point. But now x is increasing by 1. However, remember, we're going from 1 to 2, and it's going from 0 to 1, so it's actually t minus 1. And then finally, the last function, when z is moving, x of t is stuck at 1, y of t is stuck at 2, and z of t is now t minus 2. We'll call this z3, these z2, and these sub 1 for the first c1 intervals. So this is a parametrization of the movement here. So what does parametrization of a curve do? It creates an orientation to the curve. For example, in this one above, the curve is oriented in such that the positive direction is from 0, 0, 0, following the curve, to 1, 2, 1. Because, I mean, it just has a direction moving that way. Now, what else will we do in this section? We'll study a new type of integral called a line integral, where you integrate over a piecewise smooth curve, C, with respect to f of x, y. To introduce the concept of a line interval, consider the mass of a wire of finite length given by curve C in space. The density of the wire at a point is given by a function. By introducing partitions, we can deal with limits, and limits, of course, always lead to integrals. So the mass of the wire is approximately the sum of all the partitions, masses times the length of the partitions. So the definition of a line integral from an equation standpoint is if f is defined in a region containing a smooth curve C of finite length, then the line integral of f along C is given by the integral over C of f of x, y, ds, which is the limit as our partitions go to a size of 0, and then the sum of all the partitions times their own density. And it extends to 3 dimensions as well, provided the limits exist. Now, you guys probably don't care about the limit definition. You guys generally care how you're going to do this with integrals. So let f be continuous in a region containing a smooth curve C. If C is given by the vector value function r of t equals x of ti plus y of tj, where a is less than, where t is over the interval a to b, then the line integral f of x, y, dx is really just going to be the integral from a to b, so our bounds for time, our function f of x of t, y of t, times the square, times the magnitude, the square root of x prime of t squared plus y prime of t squared dt. which gets extended to 3 dimensions as well. We'll have a magnitude multiplier. This is going to be a scalar times some function. So let's see how this works in a problem. So how do we use it? Evaluate the integral over c of x squared minus y plus 3z ds, where c is the line segment given to the right. So from the path from 0, 0, 0 to 1, 2, 1, the same one we had before. We're just going to go traditionally over the segment. We're going to do it all in one step. We're going to let t go from 0 to 1. So this is our a and our b for the integral. Now, x is going from 0 to 1, so we'll let x equal t. Y is going from 0 to 2, so we'll let y be equal to 2t. And z is going from 0 to 1, so z gets to be t as well. So let's look what our derivatives are. With respect to x, it's y prime of t, x prime of t, y prime of t, and z prime of t are 1, 2, and 1 respectively. Now it says that this integral should be from 0 to 1 of our function, but our function will be converted into terms of t. So instead of x squared, we now have t squared. Instead of y, we have 2t. Instead of 3z, we have 3t. Times the square root of all of our terms added together. So that would be 1 squared plus 2 squared plus 1 squared. So all of these derivatives, which is 6. So I'll move the square root of 6 out front. Negative 2t plus 3t is just plus t. This is now dt because of the magnitude. Okay, so this is now just a simple integral. It should become 1/3 t cubed plus 1/2 t squared, evaluated from 0 to 1, all times the square root of 6. So that's the square root of 6 times 1/3 plus 1/2, which is the square root of 6 times, I think, 5/6. So it's 5 root, I don't know why I put square root of 5, square root of 6. 5 root 6 over 6. So this is the integral of that function over that line, this line integral. So how does the line integral work? It applies to something called work, how much work is done. So the definition of the line integral of a vector field: if f is a continuous vector field defined on a smooth curve C over the interval AB for time, the line integral of f on C is given by the integral over C of the dot product of f and the derivative of r, or the f and t from chapter 11. Namely, that's the integral from a to b of our function with t's substituted in times the derivative of our vector valued function r, and we will use it in the next video.